Sir, we are live now. Please start.
Great. A very good evening to everyone. This is your course instructor, Balaji Srinivasan. I should start with an apology. This is an interaction session that I normally schedule during the second week of the course. And unfortunately, there's some logistic issues and we could not schedule it then, and it's dragged on to this long. So my sincere apologies for that. I was hoping to get in touch with you much earlier. But nevertheless, I am happy that several of you are participating through the discussion forum. You've been asking some very good questions. It lets me know that you are actually closely following the course and doing a sincere effort to learn about the course, about optical fiber sensors. So please keep that going. I would like to encourage those of you that have not participated in the discussion so far. I would also like them to participate, because this being an online course, it's sort of one-way communication. I am, of course, giving you all the lectures and the assignments and all of that, but it will be really nice if I could hear back from you guys as to how things are from your perspective. When I look at the performance of the students in the assignments, I should say that I'm not terribly happy with it. Normally, I would expect people to, score on the average 50%, but I've been seeing that every week the performance is less than 50%, so which is a bit concerning. I would certainly like to hear from you as to why that is the case. If there is anything that we could do to clarify doubts or whatever, we could certainly try to do that. We are willing to spend more time and help you out, but it has to be initiated from your side. So you have to actually tell me what the problem is, and then only we can take care of that. Hopefully you are happy with the answers that you're getting in the discussion forum. That is something that you could also probably provide us feedback in your weekly feedback. If you thought something was not right, we'll try to take care of that. So far, the feedback has been that sometimes the questions are not answered in a timely manner, and it so happens that sometimes you're trying to solve a problem for an assignment that's due the next day, and then you are really desperate to get a question clarified, and that happens to be a day that neither the TA nor myself are actually paying attention to the discussion forum. In those sort of cases, we're not able to help you in time. But my suggestion would be that you try to take care of the assignment problems over the weekend itself. So I know it's usually due on a Wednesday, and I would sincerely suggest that you don't wait until Monday or Tuesday to do your assignment problems. I would suggest that you take care of it during the weekend, and you ask the question during the weekend itself, and there is a very good chance that we will actually be able to address it in a day or two. So let's try to follow that moving forward. Overall, about the course itself, I understand that we are in the 6th week. The 6th assignment is once again due on Wednesday next week. So, hopefully you're looking at those problems and you're trying to solve them. And any questions related to that, please let us know this weekend itself so that we have sufficient time to respond to your questions. Okay, so where are we with respect to the course? I would like to, first sort of share the overall scope of the topics that we have covered, and then I would like to take questions from you. There are some questions that have been already sent to me, so I'll address those first. And beyond that, if you have questions, you can put it up in the chat box, and I will try to address those as well. So let me first share my screen. And okay, so hopefully you're able to see my screen. So we started with the fundamentals of optical sensors. We started with saying that, okay, it consists of a source and a receiver, and then there is some perturbation. You're trying to measure that perturbation, and you try to do that by looking at the amplitude, phase, wavelength, polarization. We said we could have all these by measuring changes in these parameters. You could possibly figure out what is the type and magnitude of the perturbation as well. And then we went on to look at semiconductor light sources and semiconductor receivers. Then, as part of semiconductor receivers, we asked the question, can we actually have a better gain compared to what we can achieve using a PIN photodiode? So we went on to looking at avalanche photodiode. And of course, we also recognize that with avalanche photodiode, there is this excess noise factor that you have to deal with. So that is something that you have to optimize. You have to optimize the bias voltage so that you have the right, you're not incurring too much of this excess noise from the APD. And then we looked at the design of optical receiver. We looked at the direct load configuration as well as the transimpedance amplifier configuration. We looked at limitations in that. And then we went on to looking at noise in optical receivers. We are trying to understand the sources of noise, short noise. We talked about thermal noise, and did an overall noise analysis, which included the noise in the operation amplifiers. And then we went on to look at the performance metrics of a sensor. So we talked about all these different metrics and how to define each one of those metrics. We looked at that. And then went on to looking at noise mitigation techniques. So we said averaging is one way of doing noise mitigation, which could also include run length averaging. And then we went on to looking at another common sort of approach, which is filtering, spectral filtering. And we talked about specifically the use of a Savitsky-Golay filter. And then we said probably the best of them all in terms of noise mitigation is wherever possible, you can try to use lock-in detection. We looked at that principle of lock-in detection, including the quadrature lock-in detection. And at that point, we were done with all the fundamentals of optical sensors. Then we started looking at how to build, how to design an optical sensor. And we started looking at examples, as in the case of amplitude modulated sensors. And with an amplitude modulated sensor, the setup is typically fairly straightforward. We started with looking at absorption spectroscopy, differential absorption spectroscopy, and then went on to look at pulse oximetry as another example of an amplitude modulated sensor. We are trying to quantify the oxygen saturation, which is actually something that has been of much interest in the last couple of years due to the pandemic. And so we tried to understand those principles. And at that time, I also introduced to you the concept of optical time domain reflectometry, which is a fairly powerful concept because it allows you to make measurements over a fairly long distance. It could be in the order of tens of kilometers. So we looked at how to design an OTDR, right? And beyond that, we looked at a specific example of the design of an amplitude modulator sensor. There were some guest lectures also. Dr. Anish Bekal, I remember, had given a guest lecture on how this differential absorption spectroscopy is utilized in the industry for pollution monitoring. And there was also another guest lecture by Professor Jagdish Kumar on pulse oximetry, which was also quite interesting. He was talking about some of the calibration issues when you build a pulse oximeter. But we looked at some sample problems here. In fact, so there is some question about what can you expect in the final exam. The final exam is going to be something similar to what we considered here. If you remember this particular session, we were actually talking about a design requirement to build a gas sensor. And then we were asked to, I was trying to sort of guide you in the process. I was asking some smaller questions as to how you're going to build it. So if you want to fast forward and look at what is going to happen in the final exam, that's what I would like to ask you to do. I'd ask you to put together a system. And of course, it's not going to be like a very descriptive, long question and all that. I will actually have questions similar to what you have already been doing in the assignments. So those type of questions I will actually post, and I would like you to try to answer those type of questions. And in doing so, in answering several parts, you would actually get the feeling of designing a complete sensor by yourself for a given requirement. So that is sort of the thinking I have as far as the final exam is concerned. So what you do in the assignments today is very, very important. If you are spending enough time looking at the assignments and trying to do well, or even if you didn't do well, you get your doubts clarified, so that if you get another opportunity at that question, you will be able to take care of that. Okay, so I'd sincerely ask you to follow that sort of practice. So then we went on to phase modulated sensor. That's what you've been looking at the last couple of weeks. So of course, we realized right off that the optical receiver, the photodiode itself, is not sensitive to changes in phase. So you typically have to incorporate a demodulator to convert phase changes to intensity changes. And one example of a demodulator is an interferometer. So we started looking at one possible interferometer, which is a Michelson interferometer. And we learned how to measure perturbations, how some perturbations here can cause changes in phase, and how that change in phase through this interferometer is converted to changes in intensity, which the optical receiver can pick up, right? So, and in doing so, we were also looking at what sort of challenges you could have in doing this phase measurements. And we looked at mechanical stability as a challenge. We looked at source coherence as a challenge. And then when we are talking about coherence, we recognize that normally you look for high coherent sources for doing your interferometry, but we looked at a special case where even a low coherence could be quite useful, and that is this application of optical coherence tomography. So if you had looked at week 6 lectures, you'd have probably gone through some of these things as well. And we'll be talking about phase fluctuations due to environmental perturbations and also polarization fluctuations. So those are the kind of things that we have been discussing lately. So that's sort of an overview for what's happened as far as this course is concerned. So we're going to carry on for another week or so with phase modulated sensors. I can quickly show you what is going to come up. So we're going to look at overcoming environmental phase noise using a particular technique called phase generated carrier. So we're going to be talking about how that is done, and beyond that, we will go back to looking at phase noise from the source itself, and then we will actually look at another example of phase modulator sensor, which is a fiber optic gyroscope. We will look at specifics of that, and then we will look at some limitations of fiber optic gyroscopes, and then we will go on to wavelength modulated sensors, and then finally we will look at polarization modulated sensors also, and with that we will wrap up the course. Okay, so that's what is coming up. So we completed amplitude modulated sensors, some examples. We're looking at phase modulated sensors right now. And beyond this, we will look at examples of wavelength modulated sensors and polarization modulated sensors. Okay, so let me now switch and try to look at some of the questions that has come up. I know you may not be able to read these questions, but that's okay. I will just read it out for you. So one of the first questions is it difficult to interpret the result of signal when we use APD compared to PIN photodiode? The basis for the question is that APDs we know are likely to be noisy. I was mentioning that the avalanche gain itself is a random process. So if that is the case, then is it like at some point we may get some responsivity, at another point you might get some other responsivity, and so on? If the responsivity is fluctuating, then how, whether we are better off using a PIN instead of a APD? So thank you for that question. Let me just try to clarify what we are talking about here. So I think I'll go all the way back to maybe the first couple of weeks of, I think the second week is when we were talking about APDs and the gain and all of that. So let me just quickly discuss that. So I did mention that this process of avalanche multiplication is a random process. And because of that, there will be some changes in the gain. But whatever changes in the gain, it's actually following a probability distribution, typically a normal distribution. So what that means is you will get some mean gain, right? So you will get an average gain, and then there will be some variance around that gain. Okay, so for example, you can actually have an APD, the typical gain value, you can operate it as like 10, M equal to 10 for an indium gallium arsenide photodiode APD. And when we're talking about M equal to 10, on the average, you'll see M equal to 10. But if you try to look at things in a much shorter time scale, if you go down to like maybe nanosecond time scales, you will probably find that there is some variability in that gain value. So that 10 may be fluctuating between 9 and 11 and so on, right? So that is what we have. But on the average, if you do time averaging, m equal to 10. So it's still giving you much higher responsivity compared to a PIN photodiode. So that way, avalanche photodiode is certainly, very good. It certainly gives you this higher responsivity. But we talked about this excess noise factor, right? So you could potentially incur some noise, and that noise is defined by this operating point over here. So we said if you try to get very high value of gain for in indium gallium arsenide, if you try to get more than 20 gain, you're going beyond this knee point. That's when you get hit by your randomness. But until you get to that point, the noise, the excess noise that you incur is not a major aspect. And because of that, you don't really have to, the APD is still quite useful up to that point. So that is what we call as the optimum bias point. And that is what we call as the optimum gain as well. And so APD can be used reliably until that value of gain. So like I said, whatever variance that you get is a noise factor, but that's actually fairly small until you get to values greater than that. So hopefully that answered the question. Let's move on to the other question. In OTDR concept, we get Rayleigh backscattered signal, which can potentially give us information about the loss in our system, I suppose the loss in the fiber. My question is, just like we can tune many factors, cannot we tune Rayleigh scattering so that it can be, it can be a long length, it can be applicable over, you can get signals over a long length of fiber, because so you can extend your range of your measurement. And this person had actually mentioned this similar to Bruin or Raman sensors. So I want to clarify one point. Raman sensors are, the Raman scattering coefficient itself is actually much lesser compared to the Rayleigh. So with Raman scattering, you are not typically able to go to very long distances. With Bruin, you could possibly go to longer distances, that because of a process called stimulated Bruin scattering. We have not come to that point yet. That will be discussed later on in this course. So we will keep that aside for now. But going back to your question about Rayleigh scattering, can we tune the parameters such that we can go over longer distances? What I would say is that Rayleigh scattering is actually an inherent process that's happening in the fiber because of the microscopic changes in the density of the material. So normally you don't try to increase Rayleigh scattering, because if you increase Rayleigh scattering, that means that the forward propagating signal is diminished quite rapidly. So we cannot tune that fundamental quantity. All that we could do is at the terminal side. You can increase your pump power to some extent. We talked about going up to 100 milliwatt type of power levels, beyond which nonlinear effects come into the picture. So you try to limit to that. You can try to reduce the losses in your, in the different devices, and you can try to improve on the sensitivity of your receiver, which is typically one of the key aspects of building an OTDR. So you try to get a very low noise receiver with a very good sensitivity value, so that you can get to longer distance measurements. And in fact, there is a related question. So the most important thing to keep an eye in the OTDR concept, the OTDR makers formula, is the receiver sensitivity. That's the question. And I would say, yes, absolutely. This is what you are trying to actually improve upon. And you're trying to, I think, going back to what we were looking at here, I'll have to go down to look at the OTDR. Right. So we were talking about the OTDR makers formula. So you try to get as low a sensitivity as possible so that you can make longer distance measurements. Okay. So that is the probably the thing that is most I shouldn't say it's easily achieved, but that is one that's completely under your control. So you can choose a receiver, you can choose a photodiode which is giving relatively no noise, and also a receiver design that is actually giving you relatively low noise. And of course, you do the best you can over there, and then beyond that, you are doing some post-processing so that you can further improve your signal to noise ratio, and that's how you can get longer distance measurements. Okay, so hopefully that is clear. So the other question is, how do we bias at the quadrature point? I think this is related to what we were discussing in a phase modulated sensor. We were talking about having the highest sensitivity in a phase modulated sensor at the quadrature point. So that means phase modulation or the phase demodulation is typically done by comparing two different or two light sources, right? Or two different light waves. And we said we should start at a point where they are pi/2 out of phase. That's where you can get maximum sensitivity in an interferometer. So how do you do that? Is by, you don't have any control on your measurement. That arm can actually be, I think when we are talking about a Michelson interferometer, for example, if this is the reference arm and this is the perturbation arm, you don't have much control on what's happening in your perturbation arm, but in your reference arm, it's very much under your control. So you can fine tune the position such that you are actually starting at quadrature. So you are at a halfway point as far as the interference is concerned. And then if you are at that point, then you can actually measure small changes in the phase with very high modulation of the intensity. Okay, so that is what we call as the quadrature point, and that's typically tweaked by tweaking your fine-tuning your reference. Okay, so that's that. This person was appreciative of the course. It's an amazing course. Thank you for that. And then question is, please tell us about wavelength modulation spectroscopy and how it is different from differential spectroscopy. So thank you for that question. I suspect I did not talk very much about wavelength modulation spectroscopy. So this is once again in reference to what we were considering. Maybe I briefly mentioned about that over here. So differential absorption spectroscopy, I'm just looking, trying to see the right picture that I can use. Sorry, I'm going the wrong way. So when we were talking about differential absorption spectroscopy, we were looking at making a measurement at the resonance and making a measurement outside of the resonance. And we were trying to estimate the gas concentration or any analyte concentration based on the intensity measured at these two wavelengths. Now that seems like a fairly simple process, but for the fact that between these two measurements, there is always a possibility that something is changing. And maybe the concentration level, the light intensity that you're collecting, maybe there is some disturbance in the setup, and that could actually give you wrong measurements. But what we do in wavelength modulation spectroscopy is that we are modulating the wavelength around the resonant wavelength. And when we do that, we see that as you go through one cycle over here, you are actually going down and then you're coming up again. So you're actually going through, by going through half a cycle here, you go through a full cycle over here. And in fact, a full cycle over here would correspond to 2 cycles over here. So you are actually getting modulation at 2 FM. You will get this 2 FM component only when you are hitting this resonance. For example, if you are not at the resonant point, if you are somewhere, let's say at the slope, when you do this modulation, you will get only a FM component. You won't get 2 FM. Okay. So this is actually a very smart way of doing your spectroscopy, that if you are looking for 2 FM, that can happen only at a resonance. Okay. So that way, wavelength modulation spectroscopy takes out any uncertainty in your measurement due to, let's say, background variations in your intensity or variations in your coupling and all of that, right? So that and so this is sort of unambiguously measuring the absorption. And if you listen to what Dr. Anish Bekal was mentioning in his guest lecture, he was talking about this specific point, that wavelength modulation spectroscopy is the widely used technique for all their industrial gas monitoring applications. So yes, from that perspective, this is better than what you can achieve with differential absorption spectroscopy. Okay, hopefully that answers the question. Then the next question is once again with respect to OTDR. Won't we get fluorescence emission as backscattered signal during OTDR, which will mislead us getting the required result? Okay, so I suspect there might have been some confusion about the OTDR, how we understood what's happening with the OTDR. So let me just go back and just briefly review that. So in OTDR, we are basically sending a pulse of light, and even as it propagates through this long length of fiber, we were saying that it's going to scatter light in the backward direction all along the length of the fiber. And that scattering is what we have defined as Rayleigh scattering is the prominent mechanism for this backscattered light. Now the question is, won't you have any background fluorescence in this measurement? Now, whenever you have, so when do you have fluorescence? So you will have fluorescence whenever you have an absorption event. Let's say you're actually having some doping in the fiber where which is absorbing the laser light that you're sending into the fiber. And that absorption takes an electron from the ground state to an excited state. And from that excited state, it actually comes back to the ground state with with the emission of a photon, so that there could be some fluorescence because of that. Now, what we do in a OTDR, first of all, we are using a wavelength which is not resonant with any known absorption events within the fiber, and certainly not any event that is producing fluorescence. Okay, so from that perspective, you do not have any fluorescence. Let's say, I mean, the typical application of OTDR is at, say, a wavelength of 1550. At 1550 nanometers, when you send light through a glass, silica glass fiber, you do not have any absorption that's happening, which is causing any fluorescence in the fiber. Okay, so from that perspective, that is not actually contributing, or it's not messing up your measurement in any way. But of course, you could have a condition like this sort of a condition when you have a hollow core photonic band gap fiber that we talked about, which is very good for gas sensing. You could have a gas that absorbs this radiation and fluoresces also. Okay, but that is actually very, I would say it's a very unlikely event, because a lot of these gases do not have the kind of lifetimes where they could produce fluorescence. If they produce fluorescence, let's just look at that hypothetically. If they produce fluorescence, that fluorescence itself could be our measurement. We don't have to look at backscattered light. We can look at the fluorescence that's coming back from any particular location. So that will actually already indicate the presence of the gas. So if there is fluorescence, you could target that rather than the Rayleigh backscatter signal. But like I said, in most of these cases, whatever we are dealing with, we don't have much fluorescence happening. That is not a very likely event. Okay, but a very good thought. I mean, this is what I like about teaching this course, because you teach certain concepts and people try to understand that, and based on that understanding, based on that platform, they try to reach out to a different level, right? And they come up with new thoughts. Why not this? Why not that? And so on. And that's the joy of teaching, is listening to people coming up with these questions, in some cases very useful ideas that goes beyond what we are telling you. So that way it's excellent. Thanks for all your questions. Please make sure you're doing that often, and you bounce it off. It's a learning process for you as well as me, because it gets me thinking about some things that I had not thought of before, maybe, and you could challenge me to give you an answer that way. So the last question here through the forms is that whether assignment type questions will be asked during the final exam. I think I already addressed that. Yes, it will be similar to the questions that you are solving in the assignments. But even in the assignments, you saw some questions which are like, there is a common data given, and based on that data, you had multiple questions asked. You can expect some similar type of questions in the final exam. So there is one more question in the chat box. So the question is, in the OTDR makers equation, whether we have to consider SNIR factor in design while finding the launch power or detector power. Yes, that's a very good question. Like I said, we were talking about, just go back to that formula once again, just to refresh others' memory. So we were talking about the OTDR makers formula. So the question is whether we whether we look at SNIR as potentially one of the factors that we take care of the design before we think about what laser power that we use. And yes, that is always nice. So we tend to think of everything sequentially. We say this is where it started from and this is where it's going. So we'll first think about the laser, then think about the circulator, and then think about the fiber, and then the receiver and all that. It helps to invert that thinking. You start from the receiver, you start from the post-processing, you say, okay, the measurement has to happen within 1 minute, rather 60 seconds, right? If you have 60 seconds, then you think about what can I do in that 60 seconds? What are all the possible things? My measurement, my single measurement may take only a millisecond. So what can I do in 60 seconds? You can think of all your ideas as for what sort of post-processing you could do. And you say, okay, if I do that sort of post-processing, this is the improvement in signal to noise ratio that I can get. And then you say, okay, what is the signal to noise ratio that I expected the receiver? Okay, what is the receiver sensitivity? And so it helps to work backwards and then find out what is the laser power that you need to use. So unless you really have to push your laser to, you may not need 100 milliwatts, maybe 10 milliwatts is good enough. So that might actually mean that there is some savings in the cost of the laser. Okay, so those are things that you can look at. So by all means, like I said, you can start from SNIR and work your way backwards, and then say what is the requirement from the source. Okay, and this is something that is commonly done in communications actually. When we talk about the communication link design, we talk about bit error rate, and to achieve that bit error rate, we talk about requiring a certain sensitivity, and so you try to meet that sensitivity using your receiver design, and then work your way backwards and say, if this is my loss in the link, and then if I put all of this together, what is going to be the source power, right? That's how you work backwards in that design, and that's the same thing you could do here as well. Okay, I think I have answered all the questions that have come up so far. Is there any other questions in the YouTube chat box? Is anybody following that? Loss in the link, and then if I put all of this, sorry, I'm just checking the YouTube chat box. I don't see any questions there. So, so if that's all we have, then I should thank you for your presence here, and thank you for taking the course, and hopefully, like I said, you're learning from the course, and I just encourage you to ask more questions in the discussion forum. There's some brilliant questions here as well in this live interaction session, but you don't have to wait for one of these sessions. You could start asking your questions in the discussion forum itself, and let's have a discussion there. Typically, you ask one question, I respond, and then I don't hear back from you. So I would love to have a conversation going there as well. So please do that. But one more, I do plan to have one more interaction session, let's say in about 3 to 4 weeks time. But if you like this session and you say, I would like to have more of these, maybe even on a weekly basis, I don't mind going forward. We could do that. But please communicate that to me clearly through the discussion forum, and then we can act accordingly. Okay, so with that, let me close this session. As some comments, I think, in the chat box. Somebody's appreciating the assignments, and I should make a point of actually acknowledging the efforts of the teaching assistants here. So one of them is here, Anand is here. and there are the others, Subrata, Neetu, Suresh. They're all actually working in the background to provide you with the assignment questions and the solutions to the assignments and all. So without their help, this wouldn't be possible. So a big thanks to them as well. Okay. Thank you. Balaji, I think we can